This lesson is the derivative of inverse trigonometric functions. There are two notations commonly used for the inverse trig functions. We'll address the inverse sine here, the same notation that applies to the inverse sine is also used for the other five inverse trigonometric functions. So we say that sine superscript -1 of x is a notation for the inverse sine function. Another is ARC-SIN, arc sine of x. Both of these are used in many textbooks, and so you need to be familiar with these. I want to point out that this is not sine to the -1 power. This does not mean 1 over the sine of x. This is sine superscript -1 of x, the inverse sine. And we are going to use this notation in this lesson. Okay, so this means the inverse sine of x. We see that. Now, each of these two notations have their own strengths and weaknesses. We're not going to discuss that in this lesson. Move on to something that you've had before, or should have had before, and that is this property. If you have f of x and f inverse of x, f of f inverse of x is x, and f inverse of f of x is x. Let me see if I can clarify this. Follow. The square root and the square, those two functions are inverses of each other. Okay. Now, so if we take the square root of x squared, we get x. And if we square the square root of x, we get x. That's what we're talking about here. Use an example for this. The square root of 4 squared, and 4 squared was 16. The square root of 16 is 4. And also, if we have the square root of 4 quantity squared, the square root of 4 is 2, and 2 squared is 4. That's what we're saying there. That's not a proof, but that gives you a concrete example of what this is saying. So this is a tool we're going to use throughout this lesson and many times in this series of calculus lessons. We're going to use that fact right now. We have y is the inverse tangent of u, where u is a function of x, and we would like to find the derivative of y, that is y prime. So let's begin. Y is the inverse tangent of u. That's just stating that that's a given. Now, what I'm going to do next is I'm going to take the tangent of each side of the equation. Of course, that will give me the tangent of y, and this will be the tangent of the inverse tangent of u. Okay, that's all I've done that. We're telling you as we go along what we did for that step. Now, that's going to equal, say that the tangent of y is equal to u. Why? Because this is f of f inverse of x. When you take f of f inverse of x, you get x. So the tangent of the inverse tangent of u will simply be u. Next, we're going to take the derivative implicitly of this expression. So the derivative of the tangent of y is the secant squared of y. Put a y prime with it, and the derivative of u is 1. Put a u prime with it, or du. Now we'll solve for y prime. That's what we want, y prime. So y prime is u prime divided by this quantity, which is the secant squared of y. Now, earlier in a trigonometry course, you should have had this trig identity. 1 plus the tangent squared is the secant squared. And so in the place of the secant squared, we're going to put 1 plus the tangent squared. We're almost there. Notice the tangent of y is u. See this in red up here? So we're going to substitute u for the tangent of y. And of course, this is a tangent squared of y. So this will be u squared. So y prime is u prime over 1 plus u squared. And we're done. We wanted y prime. We have y prime. So here's a formal statement of that rule. The derivative with respect to x of the inverse tangent of u, where u is a function of x, is equal to the derivative of u over 1 plus u squared, or 1 over 1 plus u squared du. So that is the derivative of the inverse tangent of u. And now we're going to see how this works through some examples. Now remember the spirit, if you've been looking at this series of lessons, the spirit of this series of lessons is to teach you a rule or concept, which we have done here. We've taught you or expressed to you the derivative of inverse tangent of u, and now we want to use it, but not just use it, we want to practice it with other things that we've previously learned to help drill those into our math vocabulary. And that's what we're going to do in the examples that you see before you. We're going to revisit the product rule, the quotient rule, equation of tangent lines, the second derivative, implicit differentiation, things of that nature. So let's begin with this first problem. Y is the inverse tangent of x cubed. Find y prime. Now remember, u is x cubed. We state the problem. Now, when we take the derivative, we have the rule that says it's the derivative of u. Well, u is x cubed, so the derivative is 3x squared over 1 plus u squared. That will be x cubed squared. And of course, x cubed squared multiply exponents is x to the 6th. And we're done. So that shows you concrete how this, in a concrete way, how this example rule works. One thing before we leave this problem, please note, don't make the mistake of thinking that x cubed squared is x to the 5th. Okay? Don't make that mistake. Now, example 2, if f of x is y equals x, if y is equal to x cubed times the inverse tangent of 5x, find y prime. So we need the product rule here. So let's begin. We'll restate the problem. Now let's use the product rule, which is the first x cubed times the derivative of this. Now this is my u, 5x. So we take the derivative of 5x, which is 5 over 1 plus 5x squared, which is 25x squared, plus a second inverse tangent of 5x times the derivative of x cubed, which is 3x squared. And we'll clean this up a bit and write our answer is 5x cubed over 1 plus 25x squared plus 3x squared times the inverse tangent of 5x. That is our answer. Let's use this new rule to review the quotient rule. As you see before you, we have a quotient. We restate the problem and we'll apply the quotient rule, which is denominator, x to the 5th, times the derivative of the numerator. Now here, u is x. So the derivative of x is 1 over 1 plus x squared, minus the numerator times the derivative of the denominator, which is 5x to the 4th, over the denominator squared. You see that here? And now we'll clean it up a bit. That's a viable answer. Or you have an x to the fourth, an x to the fifth. You might factor out an x to the fourth, and then you can cancel if you see to this x to the fourth into x to the 10th, making this x to the sixth. And so we have that answer. But at least get to this point right here and work at getting to this point as you feel stronger in working with calculus. Example 4 is going to review the implicit derivative. So we're given this x squared plus 1/2 inverse tangent of y squared equals 3x minus y. Find y prime. We restate the problem here, and then we derivative x squared is 2x. Derivative of this quantity is going to be, well, the derivative of y squared is 2y, but notice we have a 1/2 in front, so we're going ahead and take 1/2 of 2y and call this y. Okay, over 1 plus y squared squared, which is y to the fourth. Now this is a y term, put a y prime with it. The derivative of 3x is 3, the derivative of y is 1 with it. Now next we will get all y primes on one side of the equation, so we'll move this over here, and the non-y primes on the right-hand side of the problem, move the 2x over like this. Next, since we have y prime on each of these terms, we'll factor the y prime, leaving us with this. That goal is to find y prime, so we'll divide this by this quantity right here. So that is an answer. We're going to take it one step further and encourage you to learn to do this. This is called a complex fraction. We've mentioned this in other lessons. A fraction whose numerator or denominator contains a fraction. This does. What we're going to do next is we're going to multiply through by the numerator and denominator by this denominator, 1 plus y to the fourth. And notice what happens when we do. When we multiply the numerator by 1 plus y to the fourth, we simply get 3 minus 2x times 1 plus y to the fourth. But when we multiply the denominator by 1 plus y to the fourth, the 1 plus y to the fourth cancels with 1 in the denominator, leaving us with y. And then when we multiply 1 by 1 plus y to the fourth, of course, we get 1 plus y to the fourth, and we'll rearrange it to look like this. And this is probably a better answer, but the course of learning get to this point. That probably shows that you know the quotient rule, and you of course know the derivative of the tangent function. In number 5, we're going to review taking the second derivative. We have simply the inverse tangent of x. We're not going to make this complicated, just to review you on what happens. The derivative is the expression. The derivative of the inverse tangent of x is the derivative of x, which is 1 over 1 plus x squared. So that's the first derivative. For the sake of finding the second derivative, we're not going to use the quotient rule. We're going to write this as 1 plus x squared to the negative 1 power. And now we'll find the second derivative. Take the derivative of this, which is going to be negative 1 times this quantity to the negative 2 power times the derivative of our quantity inside parentheses, which is 2x. And we'll write this, rewrite this like this. So this is a good answer right here. That's a fine answer. And this is a fine answer. So that completes that example. In example 6, we're going to write the equation, find the equation of the line tangent to a graph of the function. So the function is, again, we're keeping this simple. Y is the inverse tangent of x at 0.1, comma power of 4. And inverse tangent of 1, which asks the question, what has a tangent of 1, and that's power of 4. That's what the inverse tangent function does. We're not talking more about that, but that you should have had you studied trigonometry. So this point does lie on the graph. When x is 1, the inverse tangent of 1 is power of 4. And we're going to try to leave the answer in the form of y equals mx plus b, but if that becomes difficult for you, cease or stop. That's only so that we can, if we want to check our work, we can through graphing. So let's begin this problem. Here is our function. Now, the first thing we need, we have our point. So we need the slope. So we need the derivative. We not find slope. Derivative of this is derivative of x over 1 plus x squared. Okay. And now we want the slope when x is 1. So we will substitute 1 in for x. And when we do, we get this, which gives us 1/2, which is the slope m. So we'll use our point slope formula, which is this. Have to use this whenever we're writing the equation for tangent line. And now we simply substitute in for y1. It's given quantity power of 4. M, which we just found, which is 1/2, and our x sub 1, which is our given x, and that is a good answer. You might want to just solve for y and at least bring this over to the right side and do that. We've gone the extra mile and have gotten it in the mx plus b, y equals mx plus b by simply getting a common denominator. So this, it's all ready to put into your calculator to graph if you want to check to see if indeed your answer is correct. But I think if you've done your work, you get to this stage and some problems or books are satisfied getting to that point, you'll have to get acquainted with your course, find out what they want you to do. So they take some examples that utilize the inverse tangent function. So now let's see if we can find a formula for the derivative of the inverse sine of u. We want y prime. Now notice as we go through this, we're going to basically do the same thing we did for the inverse tangent. Start out by stating the problem. Then we're going to take the sine of each side of the equation. Remember, earlier we took the tangent of each side of the equation. We're going to take the sine of each side of the equation. The reason for doing that is because f of f inverse of u is u. We state that here. We're telling you in parentheses what we're doing in each step. So we have the sine of y is u. So now we'll take the derivative of the sine of y. That's the cosine of y. This is implicit differentiation. So we'll put a y prime with it. And the derivative of u is just 1 u prime, or du, whichever notation you're using there. So we have done that. Our goal is to find y prime. So y prime is u prime over the cosine of y. So we state that. And now we are going to use the fact that this, again, from trigonometry, is an identity that you probably are very familiar with, and that is that sine squared plus cosine squared is 1. We're going to take this and rearrange it and solve for the cosine of y. So we'll bring the sine squared over to the right-hand side of the equation. That means we'll subtract it, and then we'll take the square root of each side of the equation. Remember, the square root of the cosine square of y is cosine of y. Of course, this just leaves us with the cosine of 1 minus sine squared. And so we will substitute this quantity in for the cosine of y, and that's done there. And now we're one step away from being finished with this derivation. Notice the sine of y is u, so we're going to substitute u in for the sine of y, and we get this expression. Y prime is the derivative of u prime, over the square root of 1 minus u squared. there's a statement of that formula, derivative formula. Now notice, just like with the inverse tangent, the numerator is u prime. That should come as no surprise when you see us do these derivations for the inverse derivative. They all have a numerator of u prime. It's the denominator that differs. It was 1 plus u squared for the inverse tangent, and it's the square root of 1 minus u squared for the inverse sine. This one's a little more complicated, I guess, to remember. That's why we started with the inverse tangent as our first one to find. It is the easiest one, I guess, to remember. Okay, we need to know this. Let's work an example using the inverse sine rule. So we have before us y is the inverse sine of x to the 7th, find y prime. We restate this. Now this is my u, so it's u prime 7x to the 6th over the square root of 1 minus x to the 7th squared, which is the square root of 1 minus x to the 14th. So check back that we've used that formula there, and we've got an answer. The only thing we're going to do is square this, giving us x to the 14th. I think you would be expected to do that. And that takes care of that example. Now, that's the only example we're going to work using the inverse sine formula. We're not going to walk you through reviewing you on all of the things such as product rule, quotient rule, etc. Okay, we've done that. Need to move on. And so we're done with that problem. And now we want to find the derivative of the inverse secant of u. Well, formula for the derivative when given y equals the inverse secant of u. So we're going to use the same approach that we did for the inverse tangent and for the inverse sine. We state the problem first, and we'll take the secant of each side, as we did before with the tangent and inverse tangent, inverse sine. Okay. Now, of course, the reason for doing that is because the secant of the inverse secant of u is u. We state that here. Now, we're going to take the derivative implicitly. The derivative secant, remember the derivative secant is secant tangent. So it's secant y, tangent of y, it's a y term, y prime with it. Derivative of u is 1, put a u prime with it, or du. We'll solve for y prime, which means we'll divide by secant y, tangent y. We have that. Okay. Now, so what we're going to do, the secant of y is u. So we're just going to go ahead and substitute in for the secant y of u. But then we've got this tangent of y. Okay, see, everything's in terms of u and y here. And now we've got to get rid of this, get this if we can in terms of u. So we're going to use, stay with me on this. You know that 1 plus the tangent squared is a secant squared. 1 plus the tangent squared is a secant squared. We talked about that in the previous derivation, which means the tangent squared is a secant squared minus 1. Okay? You do that in your head. And the tangent then is the square root of the secant squared minus 1. So this is based on 1 plus the tangent squared is secant squared. Rearrange it to tangent squared of y is secant squared of y minus 1. And we'll take the square root of each side. And that's what we want. In the place of the tangent y, we'll put this quantity right here. And again, since the secant of y is u, we'll substitute u in for the secant of y, and it's a secant squared. So this becomes u squared. Okay. We also are going to write it as absolute value of u. And we're really not going to take the time today to explain to you why it has absolute value sign around it, other than to say that the unit circle, of course, you know the secant has different values depending on which quadrant you're in, the unit circle. And we want this answer to always be positive, and so we have the absolute value positive. Some textbooks don't include that, I've noticed. We're going to include it here in case your textbook does. And so there's a restatement of the derivative of the inverse secant of u, and you see this one's a little more complicated, but it does have u prime in the numerator, and you know the inverse sign is 1 minus u squared, and this is u squared minus 1, so you've got to keep these straight. Put a little star up here, an asterisk up here next to the absolute value sign in case you're using a text that doesn't include the absolute value around the u. Probably in most textbooks, the problems they assign you to work don't require you to use the absolute value of u, and you probably won't notice this to be a dramatic factor in working problems with the derivative versus secant of u. Let's work one problem here for the same reason we only worked one sine problem. See how this works. We have the y is the inverse secant of x to the 10th power, find y prime. So u is x to the 10th, so that's 10 times x to the 9th. And then that's absolute value of u, which is x to the 10th times u squared, so that's this, and we will square this, calling it x to the 20th. Now you notice I did not put absolute value, take the absolute value of x to the 10th, and the reason we did not, x to the 10th is always going to be positive. You raise anything positive or negative to an even power, the answer is always greater than or equal to 0. So it's not needed here. And that happens often in calculus courses, so often that, as I said, I've noticed that some textbooks drop that, but we're not. We'll make sure that better to have it and not use it than the other way around. So here's a summary of our derivative of inverse trig functions for you to have it all in one place. Now we want to do one thing further. And we're not going to derive these. It's just almost a freebie. We're just going to share those with you. And that is the derivative of the inverse cofunctions. In other words, inverse cosine, inverse cotangent, inverse cosecant. Okay. The only difference between, since the sine is u prime over the square root of 1 minus u squared, the derivative of the inverse cosine is negative of that. And likewise for the cotangent, it's negative of the derivative for the inverse tangent, and for the inverse cosecant, it's the negative of the formula for the inverse secant. So that's more or less a freebie there that we're just putting it in, whether you'll come into problems in your course that use this or not. But again, it's not much effort to add this, and it's also not a lot of effort to learn it in your case, since you already supposedly know the derivative of the inverse tangent, inverse sine, and inverse secant. And so this completes this lesson. And we'll stop